Oh, hi everybody. Our project's name is Safety Suite for Electric Longboard. My name is Pouya Akbarzadeh.
My name is Alexander Krysl.
And I'm Patrick Stach.
So yeah, the first question we want to answer, what is an electric longboard? An electric longboard is a personal electric vehicle in the form factor of a longboard. All you need is some motors and a longboard, a battery, and a remote. And you have a great vehicle for 1 to 5 mile travel, commutes, as well as a very fun recreational tool. I've owned an electric longboard for many years now, and I've realized they're rather simply designed to have a few problems. First of which, no commercial electric longboard attempts to discern if your wheels have slipped, lost traction, and you might be careening out of control, or that you're even on top of the board. No electric longboard on the market attempts to discern if you're even on top of the board or not. And then furthermore, some electric longboards don't even tell you how fast you're going, how much throttle you're implying, and you can be going fast and not even realize it. So these are all hazards we've identified. So here's a visual representation of that first issue, wheel slip. In the GIF here, we can see that our electric longboard is going fast, and then we brake so hard, the rear wheel is spinning. Right now, it's spinning out of control, and it's so out of control, in fact, we almost think it hits our camera, which is why we reach out for it. This is a serious concern. And to further drive home the point, there have been studies done on personal electric vehicles, unfortunately none on electric longboards, but for a close cousin, the electric bike, is the number one cause of injuries and accidents is wheel slip, loss of traction, and similar kind of conditions as illustrated in these studies shown on screen. Pouya is going to talk about the next issue.
Yeah, thank you, Alex. So another issue that we notice is that loadless acceleration. So let's say the user has fallen off the board, or they're just not on the board and they try to accelerate the board will accelerate at full throttle without any concern that there's no one on it to control it. And that can be clearly seen in the following video. Go. So in the video, as seen, we push full throttle on the board with no one on it, and the board flies off, and that could fly into other pedestrians and into oncoming traffic when the user has fallen off, perhaps, and is clenching onto the remote. Oops. And another issue that we saw in the same video is the limited amount of communication to the user through the remote. The remote only has 7 LEDs, which doesn't tell you much about what's going on with the remote and your board, and we think that is a big issue as well. And Pat's gonna give us some of the solutions for the issues we just mentioned.
Thanks, Pouya. So there's 3 main categories for solutions. One focus for the rider, so detecting the wheel slip, and then traction control, throttle adjustments. And then for the pedestrians, we have the user ejection detection and throttle control dampening for the situations like the video where full throttle and board flies out. And communication for the user, we have the remote display with the wheel RPM and throttle information. And then Alex will talk about features.
Okay, thank you, Pat. Yeah, so some of the features that we also added on top of the safety suite: visual feedback on the remote, telling you everything that you need to know, as well as a throttle dead man switch, which is a button on the remote you have to press in order to even engage any throttle. So if you drop the remote, we take care of that. No button press, no throttle. As well as, since we're measuring RPMs, we have a push assist control. The board can help you push the board can help you push, as well as audible feedback from the board for unexpected conditions, and as well as mode switches. We can turn off these safety features we added should the user ever desire.
And all those solutions and features allow to set up the following objectives. The 4 objectives for our project was to 1, detect the user ejection, detect front wheel RPMs, smart throttle with traction control, and communicating data to user. And Patrick's going to go over a high-level block diagram.
So what's going on here, that there's 2 main systems. There's the remote system and there's the board system. So these systems communicate with each other with their respective control subsystems with the transceiver module. And then for the power subsystem in the remote, you have the lithium-ion battery and the battery management system with voltage regulation. And then you also have the UI subsystem with just the OLED and the input and the deadman switch. And then you also have the drivetrain and power system in the board. And then you have the battery pack, which is powering the speed controller, which also the rear wheel motors are going to be getting a PWM signal dictated from the board microcontroller control signals. And also for the sensing subsystem, we have the weight sensors that are for the user ejection detection, the Hall effect sensors for the RPM sensing, and the UI subsystem with the mode switches, and the piezo buzzer for user alerts. And then the control subsystem, it's what's going to be happening, the processing of the inputs and the calculations such as whether wheel slip has occurred or not. And then Pouya will be covering our first requirement.
Thanks, Matt. So just a note for the users or for the listeners, we are not going through all of our requirements since we have plenty. We're just going over the most important ones and the most easily seen ones. So for our board sensing subsystem, one of our requirements is to notice if there's someone on top of the board or not on top of the board, and that weight threshold is 5 to 40 pounds, so we don't accidentally trigger it by moving the board or carrying the board. And it can be clearly seen in this video. So the remote says user ejected on the bottom right there. User steps on, we have a little tone for it. User steps off, you have another tone. And that can clearly be seen on the remote. Which leads us to our second requirement, which Pat will go over.
So our next requirement covers the RPM sensing in all 4 wheels individually. So as you can see, Alex is just riding in normal conditions, no wheel slip. So every wheel should be going at pretty much the same speed. So you can see that the readings in the front wheels, which are the red and blue, are very closely tracking the green and orange. The red and blue are what we implemented. Green and orange is what's from the speed controller. Even under transient like changes, it still reacts fine. And I'm going to hand it off to Alex to talk about board control.
Sure. Yeah. Thanks, Pat. Yeah. So the next requirement we'd like to discuss is the hazardous case where the remote disconnects actually from the board. And in that scenario, even if you've been applying throttle before that happens, we make sure to kill it as it's the safest option when we don't know what the rider is trying to do. So the video will play. Oh, there you go. Yeah, here we go. So yeah, so I'm actually applying throttle with no one on it. You can see the wheels spin, and then I will turn off the remote. And within a second, throttle's killed and the motors don't spin any longer. And then when we turn on the remote, we get our control back. Just a safety feature requirement that we had. And then, yeah, the next board control subsystem requirement we want to discuss is when no one's on the board, that we ensure that even if you apply full throttle, the board can't go faster than what we determine to be like a walking pace. So you can see in this scenario, I'm applying full throttle, no one's on the board, and the board just goes at a very relatively slow pace, especially compared to the original video where we show the hazardous case where the board flies away because it doesn't understand if anyone's on it. I know, I'll pass it to Pat for the next requirements.
And then for the requirements that I'd say are the bread and butter of the project are detecting whether wheel slip has occurred and correcting it. So you see the situation here is you're going fast forward, and all of a sudden you pull full reverse throttle to brake. You can see the RPMs real time on the left side. So the traction control off. This is a commercial longboard like the boosted longboard. What happens is that as soon as you brake, the wheel starts slipping backwards and it just keeps losing traction and nothing happens. Now traction control on, like the top, you see that it starts to brake now, but it's going to slow down and it's going to pump it again. So this pretty much is acting like an ABS. And to further illustrate this point, on the left, we have traction control on. And what happens when you start braking is those waveforms that are spiking down, those are the rear wheel motors spinning in the opposite direction. So you see that it's pumping and it's braking, and this is the best way to regain the traction. On the right side, however, the traction control off, you start braking and the wheel slip, you have those rear wheel motors spinning in the opposite direction, and you see that there's still a huge difference between the front wheels. So you don't really have much control over there. So now I'm going to pass it to Pouya for the remote user interface.
Thanks, Pat. And for the remote user interface subsystem, we had 4 main requirements: to show the throttle, show the state of the dead man switch, and show each wheel's RPM alongside the board's battery in voltage. And you can see that clearly on the left side, where the voltage, the RPMs are. The remote in this picture is disconnected and we're in demo mode. And then on the right side, we're in demo mode 4. We can see there's some throttle being applied, and the rear wheels have some speed going, and the volt of the battery is around 45 volts. And Pat's going to talk about our final PCBs for board and remote.
Thanks, Pouya. So as you can see on the left, this is the Eagle PCB file. we actually looked at the CAD file for the remote to make sure that the PCB cutout is going to match the outline. In the middle, you can see how it fits inside the PCB, and on the right is how everything's put together. And as you can see, there's no wasted space. You have all these components here that are essential to the system, and this all closes up. And then from our V1, everything was functional. We had a working remote, but we wanted to have a product that someone holds in their hands and think, yeah, this is something I can buy. This is like a boosted remote, or even better. And then the final version of our board PCB on the left again is the Eagle file. We have mounting holes for the standoffs, and we actually 3D printed an enclosure to house this. And this also insulates the back as an extra. And you have it all populated over there. And then Alex is going to be talking about the longboard assembly.
Yep, thanks, Pat. So yeah, just a brief layout of the board. The big box on the left-hand side is the battery. It's a pretty big battery. And then on the right-hand side, the right-hand box is where all the electronics go, our motor controllers and our board microcontrollers all housed in there. On that box, you can see one large power button that you can press to turn on and off the board, as well as 3 switches on the side that allow you to turn on and off the features that we added should the user desire or for demonstration purposes. And then, yeah, so here's a picture of the board development. Our very first board, I'll argue, is perhaps a little bit haphazard. We attached with adhesives just all the electronics to the underside of the deck, but we knew pretty soon afterwards that that's not going to fly aesthetically. So we, in the next revision, we decided to increase the size of our enclosures so that all the electronics fit, and make sure we do proper cable routing such that everything is as neat as possible on the underside of our board.
And to wrap everything up, we had a lot of success, innovation, and challenges throughout this project. We set up four objectives, and we were able to achieve them: detecting user ejection, detecting wheel slip, correcting it, and providing user a bit more data. It took a lot of innovation, such as RPM sensing for the longboard wheels, adding visual and audio feedback, and also the traction control for electric longboards. A lot of challenges, such as placing of the pressure pads, we had to go through a lot of renditions of that, making sure the two-way communication is robust. And we went through a lot of renditions of the enclosures and mounting of the parts, and also COVID made everything a little bit harder. Estimated cost and commitment, we put a lot of our own money on the line. That we only got about $100 from school, and we put about $2,300 from our own money. We were really confident, and we were really passionate about the project, and we wanted to make sure everything's perfect and the best we can do. So we went through a lot of renditions of 3D printing, as you can see on to the right. We each committed more than 30 hours a week, like a full-time job on top of our schoolwork. But the experience was priceless, and we enjoyed every single minute of it. And in conclusion, the project was a success. We were able to achieve the fundamental goals we set initially. We were able to create a product we will actually want to use, and we all learned a lot. Personally, I learned a lot about electric longboards and communication protocols.
Yeah, as an example, I learned about 3D printing and CADing that I'd never done before, so I definitely loved that.
And then for me, I learned a lot about Hall sensors and how they're used in rotary applications involving how they need to be positioned and how to extract information from the waveforms they provide.
And Alex is going to talk about some of the features we want to make in the future to the board.
Yeah, put briefly, our board's not perfect, and we can definitely improve it. One of the ways is waterproofing those enclosures, or even adding a faster microcontroller so the real-time nature of our system is more responsive, and perhaps for users to have a smartphone app for diagnostics and analytics that would be more accessible, and we think that would be really cool. As well as aesthetics, most commercial electric longboards will route all the wiring inside the deck. We certainly did not do that, but we certainly would like to do that in the future, as well as more aesthetically pleasing enclosures and proper mounting. We used adhesives for our mounting. We probably want to bolt it for the final revision. These are all things we would like to do in the future for our board.
And if you want to keep up with the project, you can go check out the GitHub page, which I've linked there, or just simpler, my website, which will redirect you there. And all the demos we showed today are on YouTube on a playlist if you want to rewatch them.